That's worse.
All right, hi everyone. As we kick off our call, just for your awareness, members of the media could potentially be present on this call. And additionally, if you need closed captioning that's provided for this webinar, it can be accessed via the closed captioning button on the bottom. All right. Just wait another couple seconds. Got some attendees still joining. All right. All right, looks like it's holding pretty steady. All right, so we'll go ahead and get started. Welcome everybody to this e-week session on the Chesapeake Bay Oyster Challenge. We're going to have our speakers present first and then have time for a Q&A. So if you have questions, please use the Q&A button on the bottom of your screen to type them in. And then we'll also have some fun polling questions pop up occasionally. So just answer those if you like and keep the questions coming. So now to kick us off, we have Alexis Dickerson of the Chesapeake Bay Foundation to tell us about the importance of oysters in the bay and the problem that the Northrop Grumman Challenge addresses. So Alexis, over to you.
Hi everyone, welcome. All right, give me just a second and I will get my screen shared. Let's go and start from the beginning. All right, thanks everyone. My name is Alexis Dickerson. I do education outreach for the Chesapeake Bay Foundation, primarily in the DC metro area, but our headquarters is in Annapolis, so I go back and forth between those locations. So I'm here today to tell you a little bit about the amazing oyster of the Chesapeake Bay. So we're gonna start actually by asking a few questions, little quiz for you guys to see how much you know about oysters. So these will just be questions that you guys can just jot down your answer on a piece of paper. It'll just be answers like A, B, C, D, something like that. And that's just for your reference, and we'll go over the answers as we go. So our first question, can you guys guess about the personality of an oyster? Do oysters seem like the loner type to you? Or maybe some type of creature that's really attached to its friends or family? Or do you think it's a really social creature? So take a second and jot down an answer, what you think about the personality of an oyster. And we're going to do our big reveals after each, or at each slide, so I'm not going to go to the next one before I give you an answer. So a couple more seconds to answer. And our oyster personalities are actually social. They're very attached to their friends and family. And it's actually really critical that they are around other oysters so that they can actually grow their populations. And so we have what we call oyster reefs that are basically a connection of multiple oysters on top of each other. And the shells that they use to create their reefs are actually called parent shells. So we like to think of that as like a family relationship. So oysters are really attached, literally attached to their friends and family. Next question. What do you think an oyster might accomplish in a day of work? So if an oyster is doing a work day, what do you think it might be up to? So our first option is releasing a lot of calcium into the water to help fish build strong bones and teeth. Or maybe they're opening and closing their shells all day, trying to catch some fish for dinner. C would be filtering gallons and gallons of water every day. Or D, all of the above. So take a couple seconds, look over those options, and try to give your best guess of what an oyster might be up to for a day of work. All right, hopefully everyone jotted down their answers in their on their pieces of paper. So the answer to this one is actually that the oysters are filtering massive amounts of water every day. We'll learn a little bit more about why and how they filter water, but that is what they're doing on a day-to-day basis. They're a really important species in the Chesapeake Bay for that reason, because they're filtering so much water. All right, our last question. How do you think John Smith described the Chesapeake Bay oysters? Do you think he described them as navigational hazards in the water, something that's hard for them to get around when they were in boats? Do you think he didn't even notice them because they look like rocks? Or do you think he claimed that they were champions of clean water, since we know that they do a lot of filtering? So take a couple seconds, think about your answers, and let us know. All right. So John Smith actually described the Chesapeake oyster as navigational hazards in the water. One of the really interesting things about the Chesapeake Bay is that it is a tidal ecosystem. And so water pushes in from the ocean into the Chesapeake Bay, and that raises the water level of the Chesapeake Bay. This happens twice a day. So when that water level goes up, sometimes it's easier for ships to navigate. But there were actually so many oysters at the time of John Smith that when the tide came back down every day, that sometimes the oyster reefs would be sticking above the water or making the water too shallow for boats to even navigate. So they were actually navigational hazards because there were so many oysters in the Chesapeake Bay in John Smith's time. So we're going to talk a little bit about oysters, and one way to understand how they work is using analogies. So an analogy is really a way to compare two items or two ideas using creative or imaginative thinking. So we talked a little bit about oysters as filtering the bay. So we have this air filter, and that's an example of an analogy. So another analogy we have here is these look like a bunch of homes, and people do things in homes. They use them for shelter and protection and a lot of different things. So another analogy for what oysters do is they actually provide habitat or a home for a lot of other species of things living in the bay. Next, we have a bag of Cheetos, if we go down and to the right. So our bag of Cheetos is actually an analogy for food. Oysters are food for species in the bay as well. And last but not least, we have a picture of a fish market. And so another way to think about oysters as an interaction between humans and the ecosystem, that people go to the fish market to buy and sell things. So it provides a livelihood, and it becomes a part of the local economy. So the oysters are actually really important in the Chesapeake Bay as part of our economy. So those are some of our analogies for how we'll think about oysters as we learn more about them. So historically, oysters would actually be harvested in the wild during the winter months. That's when it's really cold. It's really tough to be an oysterman out on the water. So more recently, as the oyster populations have declined, more of our oystermen have actually started moving towards aquaculture. So this is an opportunity for people to put oysters into baskets and put them in the water. And instead of having a natural reef where the parent oysters are building on top of one another, this is just using bins and baskets as ways to hold the oysters in one place and placing them in the water, letting them grow, and then removing them that way for market. So this is actually really important for the economy of the Chesapeake Bay. This is how watermen support themselves and their families. And this is a legacy of the Chesapeake Bay, which is really fantastic. And it's been really great that watermen have been able to be flexible and change over time with the types of things that they are, the way that they are harvesting oysters. So oysters, one thing that's interesting about oysters is they're kind of a little bit like Goldilocks. They're very particular about the salinity that they want. So too salty, they might not like it, and too fresh, they might not like it. But if it's just right, then an oyster will be happy in that place. So different oysters have different tolerances for salinity. In different parts of the bay, the oysters actually taste different based on the amount of salt that's in the water and also the amount of nutrients that are in the water. So it's very specific and very custom to the Chesapeake Bay. So a little bit about history. This is a huge pile of oyster shells. That is a massive pile of shells. This is an example of how abundant oysters used to be in the Chesapeake Bay. And there's a question that popped up on the screen. If you guys want to answer that, what's your favorite seafood? There's some options on there. Hopefully all of you are choosing oysters right now. The other picture to the side is actually a picture of someone that's doing aquaculture. So if you see the picture to the left side, that's showing how abundant oysters used to be in the Chesapeake Bay, and then how we've adapted and changed over time because of over-harvesting that fishery. So at the time of John Smith, there were so many oysters in the bay that, again, ships were almost running into them as they were trying to navigate through the Chesapeake Bay. But over time, because it was such a profitable industry, people harvested so many of those oysters that we got down to what we consider only 2 to 3% of the historic population. So if you started with 100 oysters, we harvested so many oysters over time and changed the climate of the bay so much over time that there were only 2 to 3 oysters left out of 100. So that's pretty significant. So in order for people to continue to work in the oyster industry, that is why people have moved to using aquaculture. Aquaculture also allows them to grow oysters all year long, which is different than harvesting just in the winter. All right, I think I have to answer this too. I'm going to say oysters. All right. Next, let's see if I can go to my next slide. Perfect. All right. So there's a term that we use for oysters, and we consider them a keystone species. A keystone species is a species that is so abundant and so important to an ecosystem that they actually have a disproportionate or a larger effect than most species on the ecosystem that they're living in. And so oysters actually do that. So oysters, what they're doing is they're filtering in the water, they're sucking it in, and they're pulling out little things in the water called plankton, phytoplankton and zooplankton. So they're two different kinds of plankton. One is like little plant plankton and one is like little animal plankton. So they're sucking in all of that plankton, and that makes the bay change color a little bit. So if you can think of the bay as normally being a brownish green color, that when they filter it through, then it gets clearer and clearer and clearer because they're taking those suspended plankton out of the water. Oysters also provide a lot of habitat for a lot of species. We'll see that on another slide, but nearly 300 species are supported in terms of habitat by oysters. They're also a vital food source for much of the bay. So they're eating, in this picture, these are cow-nose ray, which are one of the species that live in the bay, and they are hovering over oyster beds and eating oysters. So one thing we mentioned at the beginning is that oysters have relationships with other oysters. So their favorite surface to grow on is on the shell of other oysters. This is for a number of reasons, but one of those reasons is that the other oysters already know where the primo spots are. Where am I going to get the most plankton and all the good stuff so that I can grow big and strong and healthy? So if they can find the spots where other oysters are, they have different ways of doing this. Northrop Grumman folks will tell you a little bit about some of the ways that they're finding other oysters. But oysters are naturally attracted to the surfaces that other oysters are already using. So you'll get oyster reefs like you see on the top right. And you can see that it's feeding birds. There are birds over here that are looking around for lots of different species that are hiding among the oysters. But if oysters don't have their preferred surfaces, they will use other hard surfaces. So you can see on the bottom, here's a picture of a crab that has oysters growing on its shell. So that's going to be a really bad day for that crab, but that is how flexible and adaptable oysters are when they're trying to find an environment to grow on. So they used a hard surface that they found, which happened to be a crab shell. So oysters need other oysters to grow. So as populations of oysters diminish over time, then unfortunately, it's more difficult for them to find other parent surfaces to attach to, which is a bummer. These are some examples of things that grow in or live and get habitat from oyster reefs. So on the top right, we have a redbeard sponge. So this is growing off of an oyster. Crabs love to hide, and there are lots of different types of crabs, but crabs love to hide in oyster reefs. They get protection. They can have their young there, or when they're shedding and molting their own shells, that they can use oyster reefs as a way to protect themselves from predators, because they're hard surfaces that the predators can't really get down to if they're larger. We also have things like oyster toadfish and hog chokers, and all sorts of little smaller fish as well. So oyster reefs actually become a nursery for lots of different things to hide and protect themselves. And some things have even adapted, like this oyster toadfish, to blend in with the oyster so that it can kind of lay there and hide out and camouflage and then jump out and grab other fish. So the impressive part about oysters is, let's see. Ooh, crab was our #1 winner on the panel. Thanks, guys. All right, so the #1 thing about oysters is they filter so much water. So they can filter up to 50,000 gallons every day. But at that rate, it would take about, I'm trying to, sorry, I think this one back. Ooh. All right, it's not going to show me again. So at that rate, it's filtering the bay once a year, but previously the bay could filter itself almost on a weekly basis because there were so many oysters in the bay, bringing all the nutrients and sediment out of the water column and putting those back on the ground. So this is a video. I'm not confident in clicking that and seeing if it's going to work, but I have another video. We'll try that one. All right. All right. So oysters are vital to the Chesapeake Bay, to the health, to the economy of the bay, and they're a big reflection of the water quality. So if the oyster population increases, then we have more habitat in the bay, more filtration in the bay, more erosion control and storm buffering, and fish stocks. So those are all really important things that oysters do. So the lowly oyster, this hard, kind of grumpy looking thing that you would think maybe would be a loner, is actually a very social, communal creature that's creating a lot of habitat and wonderful places for other things to live in the bay. So incredibly, incredibly important. So one of the things that the Chesapeake Bay Foundation tries to do is figure out how to preserve and save oyster populations throughout the bay so that the bay can be healthier and the economy can be healthier and all of the species can get better protection from the participation of oysters. So one thing that's really interesting about oysters is thinking about how the populations have changed over time. So in Maryland, this is a harvest based on their bushel numbers. In the 1870s, there were almost 9 million bushels of oysters that were harvested. It peaked in 1884 at 15 million bushels, but compare that to today. So 100 years later, after they were harvesting 9 million to 15 million bushels, 100 years later, they're only getting 2.4 million and then 1.14 million. And now in the 2000s, in 2000 and 2018, we have less than 500,000 oysters being harvested, and actually much less in 2018. So these populations are being severely impacted, which is why we're partnering with organizations like Northrop Grumman to monitor oyster populations, to make sure that they're healthy, and to bring them back to their historic or closer to historical levels so that they can do the work of filtering the bay. I'm gonna jump back and see if I can play this video. It might not work, we'll see. It might make me try to watch it on YouTube. All right, so this is a time lapse. This is actually just a time lapse of the oyster filtering. There you go. So let's see if I can advance the slide again. Sorry, that one didn't show up. All right, so we learned about the changing population, and that brings us to our partnership. So the Chesapeake Bay Foundation is working now with Northrop Grumman on something we call the Chesapeake Bay Oyster Monitoring Grand Challenge. So we're bringing the best science and engineering. So we have a lot of science about the bay, estuary science, and Northrop Grumman's engineers have the best technology and very creative minds about thinking how to solve problems. So the Chesapeake Bay Foundation has partnered with them to figure out how can we save the oyster populations? How do we get a better idea of what's happening to them? And how do we collaborate to restore those oyster populations? So that is all that I have for you guys. If you have questions, I think you can put them in the chat and I might be able to see them. I will stop my screen share and then that way I'll be able to see the chat. So if you have any questions, please ask. Otherwise, I will pass it back to the folks at Northrop Grumman.
Yeah, thank you so much, Alexis. And yeah, if you have any questions, we definitely have time at the end to get to as many of them as possible. And hopefully be able to email you if we don't get to some of them. But while Martin's switching over his presentation, we're going to switch to him. Martin Kozacek is the lead for the Northrop Grumman Oyster Challenge, and he's going to tell us more about the project. So Martin, take it away.
All right, thank you, Katie. And thank you, Alexis, for all that great information. And can you guys see my chart and hear me? Good. Right, so as Katie mentioned, I'm Martin Kozacek. I'm a program manager and engineer at Northrop Grumman in the Baltimore, Annapolis area. And for the last 2 years, I've had the pleasure of working with the folks at CBF in developing and now executing the Oyster Monitoring Challenge. So Northrop Grumman historically is a company that makes things like airplanes and satellites and sensors, right? We don't do a lot of technology development for conservation or environmental applications. But here we've had the opportunity to actually take the know-how we have of building cameras and radar and things that go underwater and in outer space and apply it to something in our backyard. So it's enabling us to basically take the technology that we're very familiar with and apply it to the space. So this challenge started in 2019, where we contacted some of the scientists at CBF and tried to figure out what are some areas that we may be able to help them with. And as Alexis mentioned, the oyster being a very critical species to the Chesapeake Bay is in a severe decline, as you saw the numbers. So they are essentially trying to reseed the critical mass population of oysters in the Chesapeake Bay. And to that end, they're trying to, we say plant, but these are animals, plant 10 billion oysters before 2025. And just to let that number sink in, that is an astronomical quantity of oysters that they're trying to put in. And as they're doing that, they obviously want to see how these oysters are doing, right? It's one thing to just put the oysters in, but they're underwater. You can't go see them. It's not like planting trees where you can just walk out and look at the trees, see that the trees are growing, even at a very large scale. You can fly an airplane over them. This is very difficult. You saw the video that Alexis showed of how the oysters clean the water. The water in the bay is actually probably a little bit even murkier than what you saw at the beginning of her video. So it's very difficult to see this. So what the scientists at the Chesapeake Bay Foundation do now is they can either send a diver down with a camera to see what, basically what the shape of the oyster reefs is, or they can actually pull the oysters out with a set of tongues, which are kind of a big rake, but that destroys the reef and is a sort of a destructive form of testing. So what we decided to do in collaboration with the Chesapeake Bay Foundation was to develop a set of basically remote sensors, things that could be put in the water, maybe on a robot or off the side of a boat, and essentially help them look through the murky water and see what's going on down there. So we announced this as a challenge to Northrop Grumman engineers across the entire company. Like I mentioned, I work here in Baltimore, but we have campuses all across the United States and internationally. And so we basically said, hey, we have this problem. We want to see, literally, we want to see oysters through very murky water. We want to help count them, and we want to see how they're doing. Are they alive? Are they dead? And we put this out to all of our engineers across Northrop Grumman back in 2019. We had received more than 10 proposals to develop this. And we had teams of, 40, 50 engineers working on these solutions all across the United States, from Maryland to North Carolina to California, and a few places in between. And so those folks, a few of them are here on the call who'll be able to answer questions, began in the summer of 2019 developing their technologies and trying to deploy initial prototypes. And a prototype is something short of the kind of thing you can go to a store and buy, right? So something we pulled together with pieces of equipment that we think would be suitable, but it isn't quite suitable yet to provide to the Chesapeake Bay Foundation to work with. So in the late fall of 2019, we actually began deploying these systems, and I'll talk about them in a little bit of what kinds of technologies we're applying here. And starting to show that, hey, we think we actually can do this, because this is not a very simple problem. And it requires a lot of different capabilities to try to provide an answer to the Chesapeake Bay Foundation, which they can then use to assess how the oyster population is doing. Folks, I think, had asked in the chat of, well, how many oysters are there? That's a difficult thing to do. You can't go down there and count them, right? And we're trying to give them the tools to be able to do that. So last year, or actually, sorry, in 2019, we spent a lot of time developing the concepts that we would apply. And then last year, those same teams matured their systems. So they developed them a little bit more. They spent time working with the Chesapeake Bay Foundation out on the water, actually putting this equipment over the sides of boat or deploying it on remotely controlled rovers to map the bottom of the Chesapeake Bay. And this year, we're planning on actually providing a good portion of this capability to the Chesapeake Bay and actually a broader organization that they support, so they can start monitoring the health of the oyster reefs in the bay. So what are we doing to address this problem? As I mentioned, the water in the Chesapeake Bay is very murky, and how many of you, and it might be difficult to see, but how many of you have snorkeled in the past? Or have been underwater? You can just type in something in the chat box. Let's see if I can even see it. Well, if you've been snorkeling or you've been diving, obviously you're down there to see the fish, the corals, and things like that. If anyone has done that in the Chesapeake, it's very hard to do that. I've been I haven't done a lot of diving, but it's really hard to even see your hand significantly in front of your face. So if you're trying to look at oysters, you would have to get down to them, but first you have to know where they are. So one of the sensors that we're developing to find reefs and kind of map them is something called a sonar. And for those of you that aren't familiar with a sonar, it was actually a technology developed based off of the way that dolphins and whales and other animals like that communicate, where they send out these little clicks and whistles, which I'm sure some of you are familiar with, and then they listen for the echo. And a sonar is basically a piece of technology that does that. So our engineers took a sonar, not too different from the kind of thing you might use to find fish, for example, if you're into fishing, and figured out a way to adjust it so that you can map the sea bottom, which is difficult in the Chesapeake because there's a lot of other things down there that look like an oyster, right? Oysters, mature oysters are about 3 inches across, which is not too different from a rock. And so it's hard to know if you're seeing a rock or an oyster, but they essentially taught a computer to take an image from a sonar, which you can see here on the left, right? It just looks like kind of a grainy speckled sort of, it's hard to tell what's what, but they actually taught a computer to take that image and be able to, based on looking at prior images of a reef, to tell if it's looking at oysters or just rocky bottom or just something different. So now the folks at the Chesapeake Bay Foundation can tow a sonar, which is kind of the size of a watermelon, behind their boat, back and forth, kind of like mowing the lawn, and map the bottom of the Chesapeake Bay and see where the oyster reefs are. And with that information, they can kind of assess the overall size of a reef and not very accurately how many oysters might be in that reef. So then the next thing they want to do is say, okay, well, there are oysters down there. So are they healthy oysters? Are they alive? Are they dead? And an oyster reef is actually very similar in one way to a forest. If any of you have ever been to a forest that's very healthy or vibrant with life, you will hear birds, maybe some squirrels, the trees rustling, as opposed to a forest that's dead would be very quiet. And you may not think it, but an oyster reef is very similar. Alexis had showed you the oyster toadfish. It makes a very characteristic honk that you can hear. There are snapping shrimp that live on oyster reefs, even as far north as Maryland, and they have a very loud kind of a snap that they produce. And we can listen for these sounds. And interestingly, oysters can listen to them as well. And so an oyster, a little larva, right? So a little tiny baby oyster, as it's sort of making its way through the water, it can not hear in the way we hear, but it can perceive or kind of hear the sound of a healthy reef. And when it does that, it'll say, hey, I should settle here. And it can swim down through the water column and basically that says, this is my new home. And we can listen for that as well. And then we can tell the scientists at the CBF by putting in these underwater microphones that, hey, this reef seems healthy. So as they take their oysters that they grow in the lab in these giant tanks, they know that if they put them on this reef is doing well, it's healthy, and it might give those oysters a better chance of surviving. And so then the final thing is you really want to go down there and see what the reef looks like. And like I said, the folks at the CBF can send a diver down, but there, as we mentioned, the Chesapeake Bay is an intertidal zone, meaning that the water comes in and the water goes out. Sometimes those currents are pretty tough to navigate. It's hard to swim with a camera. So putting a diver down there is a little bit dangerous. So we're working with them to create camera systems that can basically see through the dirt in the water. So the human eye can't see it, but these cameras enable us to basically see through the dissolved sediment, the plankton that's in the water, and figure out what's on the other side. So we were using initially two different kind of technologies, one which is based on a laser system, and another one that basically takes a very clever camera that has the lens kind of like a fly's eye or an insect eye that has many, many, many different little lenses on the surface. Each one looks at the image in a slightly different way, and then you can train a computer to basically reconstruct that image and take out everything that's in between where you are and what you're looking at. And so the result is you can sharpen and improve the image of what you're actually seeing. So these kind of systems and technologies we're planning to provide to the Chesapeake Bay Foundation and other organizations to help them monitor the health of the bay. So a big part of the work that we do here is developing these concepts. It's writing software in the lab. It's building the physical structure of a machine. So welding, bolting together mechanical pieces, assembling sensors like cameras and underwater hydrophones, which are kind of a microphone. But then at the end, we have to go put this stuff out in the field. And it's really amazing to be right here on the Chesapeake, where we can essentially take what we build in the lab, go out on one of our research vessels and put it in the water, working together with the scientists at the Chesapeake Bay Foundation, and kind of firsthand see what works, what doesn't work. You go back in the lab and we fix it, and we go back out. So you can see here in the image some of the engineers working at Northrop Grumman with actually the camera that I mentioned. So you have to take the camera, you have to put it in a vessel that allows it to stay watertight. You have to put on lighting, and all of this other work that's required to take something from a concept and actually be able to deploy it in the field where you can't see it, right? It's not, you can't walk up to it and just and kind of change some settings. Everything has to be done remotely. You're down working 15 to 20 feet below the water surface. So there are all kinds of interesting problems that we have to solve. And we've spent a fair amount of time and plan on doing a lot more this spring and summer, working with the folks at the CBF to actually test the hardware that we've built and collect more data in hopes of refining the system. Here are some additional pictures of folks actually testing the sonar system that I mentioned. So this is a a little piece of equipment that essentially acts, like I mentioned before, kind of like a dolphin or a whale, and you tow it behind the boat, and it essentially shoots out acoustic sounds, which we can't hear. The frequencies are much higher, and then looks at the reflection from the bottom. And these are things you can just buy in the store, but we're helping figure out new ways of taking the data from these instruments and making it, providing the answers that the folks at the CBF are looking for. And oops.
Hey Martin, just real quick, we're not seeing the slides advancing. Could you reshare and go into presentation mode?
Uh-oh. That's not good.
There we go.
Oh, it did come up now? Okay.
Yeah, now it's advancing. Could you pop it into presentation mode?
I did. I think I know what the problem is. Hang on a second. I'm sorry about that. I think I need to reshare my screen.
No worries. In the meantime, let's do a poll.
Here we go. I think this should work. Let me know if you can see it now.
All right, there we go.
Okay. Well, I'm sorry about that. So I will skip back a little bit. So as I mentioned now, if you can see, I think this is Simone testing the light field camera in its watertight enclosure. Then we have Jason, who I think is on the call as well, working on the sonar system. This was all done here on the Chesapeake, just outside of the Bay Bridge. And then obviously there's it's not just hardware. We have a tremendous amount of software that basically takes the data from these instruments and converts it into something that someone can make a decision based off of. So we spend a fair amount of time figuring out how to apply technology, but then create an answer from it. That's really at the end of the day what we try to do. So moving forward, our goal is again to enable the Chesapeake Bay Foundation and other similar organizations, because it turns out this problem is not just a local Maryland problem. We're working with another organization in the United Kingdom, in England, that's looking to reseed their oyster reefs, which are similarly depleted, and Australia. So the oyster, something we've learned is a key species around the world that's very significant to the health of our bays and coastlines. These reefs provide protection from waves and rising sea levels. So they also provide sort of a defense for our coastline, which is something that we want to support as well. So as I said before, we spent the last 2 years trying to come up with how to solve this problem. I think we've demonstrated that we are able to. And this year we plan on actually completing this work and giving the Chesapeake Bay Foundation the tools it needs to try to complete its mission, planting 10 billion oysters in the next 4 years. And then hopefully beyond that, we can figure out how to do these kind of projects in other areas. Maybe we move on to trying to look at seagrasses and other things that also help keep the water clean, help protect and improve our environment. So I think that's all I had on the presentation. Katie, I'll turn it back to you for Q&A, I think.
Okay, perfect. Yeah. So we've had a lot of good questions coming in. So we're going to do our Q&A with not only with Martin and Alexis, but we also have a couple other members of the Northrop Grumman Oyster team on here, including Jason Cochran, James Hutchinson, and Beth Martin. So hello and welcome to everybody for the Q&A. Let's get to some of your questions. So I'm kind of just talking or like piggybacking off of what Martin was just talking about. We had one question come in from Jessica, which was what different kinds of engineers work on this project and what kind of training is needed to be able to work on it. And so maybe you could talk a little bit about, what kind of training, but also what inspired you to get involved with this project, or in Martin's case, kick it off and create it.
I'll start and then I'll actually let the actual engineers talk. So I'm a mechanical engineer, but I tend to work in a field that's called system engineering, which is basically looking at all of the different disciplines. So how do you take something that's a physical component, whether that's a camera or a robotic arm or something like that. How do you combine it with a piece of software that enables it to do something, right, to actually execute a task? And then how do you determine that it's actually able to do it? So a lot of testing to verify that when you build the robot in some specific way and then you program it to do a specific job, you then stick it in the environment that you intended to do that job, and actually, see how it works. And I've been very passionate about about the environment. I've worked on some environmental satellites in the past that help monitor the Earth's climate. And so this was an interesting way of taking our very unique technology and applying it to a problem in our backyard. But I think, yeah, Jason and Beth can talk a little more about the specific kind of work they do.
Yeah, so I think one particular skill, because I'm a software engineer, right, is just the ability to create different types of things in software. There's a lot of machine learning that was involved in the SONAR portion of the project. So I think, like Martin was talking about, that systems engineering is combining hardware and different types of software together. I really focused on the software component and how do we analyze the SONAR data.
Hi, everyone. I'm Beth Martin. Similar to Martin, actually both similar to Martin and Jason, I have done some software engineering in the past and also systems engineering. But I think one thing I want to tell you all is that what we've done on this project is a lot of working as a team and working with our other engineers. You don't really do engineering by yourself. You do it with your friends, with your teammates. And what we've all done is we've got people who are really good at building things. We've got people who are good at cameras and sensors and things like that. We've got people who are really good at audio things, listening for sound. And we've got people who are good at coming up with new ideas and understanding how to take an idea and make it into a real thing. And so what we've done on this project is taken all those different engineers, all those different people, depending on whatever they're good at, right, and putting those all together. So I think that's one thing that's good to know about engineering is it really takes a lot of people and you bring your specific skill set, and then all together we've been able to, go out and do a lot of good things for the oysters and monitor them and take pictures of them and listen to what they sound like. And that's how we're going to help the CBF and help the oysters.
Okay. I've got a lot of good questions for Alexis too. So there's a lot of questions about overpopulation. Is there a concern that there could be too many oysters in the bay?
I think that's a really cute question. Yeah, the historical numbers were so much higher than the current numbers today that we are at no risk whatsoever of having too many oysters in the bay. Oysters are, they need the hard surfaces to grow on, but they also need a lot of other environmental factors to go their way. So many of the oysters, someone asked how they reproduce. So a female oyster will release eggs into the water column, and a male oyster will release, his fertilizing agents into the water. And those will kind of mix with the current. So it's a very imprecise science of how the little baby oysters even get made, which is why engineers and scientists are stepping in and they're doing, allowing oysters to reproduce in labs, growing them in small containers, and then taking them out to oyster sanctuaries so that they can grow kind of at a maximum population. But it's really difficult in the wild for oysters to reproduce successfully because you're at the mercy of the currents and all of the factors in the environment. So there's a lot going on. We're not going to overpopulate the oysters, but we can try.
Yeah, fingers crossed, we can just try. Okay, so we'll do a back and forth here. So question to the Northrop Grumman team, what's something new that you learned about the bay or oysters from this project?
Maybe I'll kick it off. I think I did not have an appreciation for how important the oysters were here and worldwide, right? I mean, Alexis talked about the way I've known oysters is food, right? I like eating oysters, and that was my relationship with them. And in working on this project, you really learn how important they are. Something so small has such a far-reaching impact on our environment here, but then in our country, the whole continent, and as we've seen, it's across the world. So for me, it was just exposure to how important they are, how endangered they are, or depleted, and that we can do something about it. So that was really, really exciting for me.
Yeah, and for me, I think I learned a lot about doing work in the underseas environment, right? For Northrop, I work on a lot of different types of airplanes and things that operate, up in the sky. So I've never actually done anything that's gone underwater. So Martin showed pictures of the different types of little robots that we use to send the cameras down to the bottom of the bay. And he also showed some pictures of different cameras and things that we've put on different harnesses and then lowered into the bay. So I think it's really interesting to learn about how some of the engineering that I apply to airplanes and things that fly can actually translate into things that go underwater.
And I know my group has been looking at the acoustic environment. So what sounds do oysters make and how do oysters respond to sound? And I saw there was a question in the Q&A about how do oysters hear? And I think that's a really good question. We were actually talking about this last week too. I think that we talked about like pressure waves and things like that oysters can, but I encourage you in your class to try to look it up, right? Try to figure that out. But one thing I do know is there's evidence that's shown that when you play sounds at certain frequencies, they have observed that oyster shells will close their shells, right? They don't like certain sounds and they do like other sounds, right? So it's really interesting to think about, what do oysters do? How do they respond to sound? What kind of sounds do they make? And if they can hear, are they hearing us, right? And as we are in their environment, right, as we take our boats there or swim in the bay or do whatever we do, how do they respond to us as humans? So I think those are really good questions, and keep asking them. I don't have all the answers for sure.
Okay. Back over to Alexis. We've got a lot of questions about how oysters clean water. So could oysters clean something like a pool or a fish tank, or water to the point where it would be of a quality enough to drink?
Very good question. So oysters basically are sucking in water from the water column, and they have like little gills and things that are going to capture the plankton that I mentioned. So the zooplankton and phytoplankton, that's really delicious, and they're minerals that that oysters need. And then the things that they don't need, they actually shoot out the clean water, and then they will clump the minerals and other things into little packets and push that out of their shells. So they'll make sure that things that shouldn't be floating around in the water column kind of get shot down to the bottom, and then they bring in clean water and shoot that out of themselves. So that is good. A pool would not be a great environment for an oyster because they're not going to be the phytoplankton and nutrients that it needs, right? So we try to keep pools really clean, and chlorine and things like that might actually be toxic to an oyster. So it wouldn't be great for that. As far as whether they can make water clean enough to drink, they are taking out some things out of the water column that usually will make it kind of cloudy or murky, or minerals, things like that. But there are other things that they probably can't take out, like toxins and E. coli, bacteria, things like that. So just because water looks really clear because an oyster has filtered it, there are some other things that you need to be concerned about. So you'd want to make sure that you were being very scientific about testing the different parameters to make sure that it's safe enough to drink.
Perfect. All right, so back over to the Northrop Grumman team. We got some good questions about the technology, and I'll put two of them to you guys. One was, how detailed are the images that you gather from the cameras, and what sort of sensing distance are you getting with the cameras? The sonar cameras specifically.
Well, sonar, Jason, I'll let you take that one.
Yeah, for the sonar, we can see maybe down to a few centimeters. So that's, maybe about kind of like the size of the palm of your hand. So we could roughly see the size of one oyster. So, and that's from maybe 20 feet from the bottom of the bay up to the bottom of the boat where the sonar sensor is mounted.
And what we learned throughout this project is, obviously there are sonar sensors that can see much better than that. They're very expensive, right? And so for a scientific organization that is a nonprofit, these are not the kinds of things that are suitable. So this has been a challenge for us, because we typically, like Jason said and like Beth said, we work on things that are meant to see really far, that are meant to look in space. Are complicated and expensive, and so the unique thing for us here was to try to see how quickly can we make something that's also very inexpensive and that still operates in a difficult environment. So while some things like that might not seem very impressive, they're actually very difficult challenges. And also, if you want to try to see something much smaller, that means you have to shoot out a lot more energy from the sonar. Which then means you'll actually go right through the thing you're trying to look at. And so there's a lot of iteration. That's why I was highlighting the testing, right? All these things sound good in a lab, but when you actually get out there and start trying to test the hardware and the software that you've built, you really get to see that. And that's such a big part of our work, and something that we get to do here very quickly, unlike some other projects where it takes years to build an airplane or a satellite or something like that. Here, in 6 months, which may not sound quick, but it's pretty quick. We got to take hardware and go out on the water and see how it works, and work with the scientists who can say, oh yeah, that's an oyster you're seeing, and now you can start teaching the computer that that's an oyster. Or if you're listening to to the acoustics, that's a toadfish. So anyway, segue.
All right, anyone else for the team? All right, so back to Alexis. We're getting a lot of questions about kind of like the upper echelons of what an oyster can do or how it can grow. So things like, what's the biggest oyster that has ever grown, like assuming it wasn't eaten or harvested, how big can they get?
That is a good question. I don't know the record, the largest ever, but oysters can start reproducing at 6 months of age, but they're considered in their best reproductive range, usually from like 2 to 6 years. So they can actually live for a very long time, and they can get very, very large if they're not harvested. So, my hand's as big as my screen. You can get an oyster that's this big. And I'm sure there are ones that are much larger even than that, if you let them continue to live. Someone did ask in the chat, and I've been responding to questions in the chat, but I don't know if it's easy for people to see their responses, that oysters are, when they're born, as soon as they kind of fertilize, they already have a little tiny, teeny shell. So even though oyster spat is what we call the little tiny baby oysters in the water, they already have a little shell, even though they're microscopic, which is kind of crazy to think about. So they're one of the ones that they grow and expand their shell over time. They're pulling nutrients out of the water column to build their shell, as opposed to something like a hermit crab or something that's going to find a new shell and get a bigger shell as it grows, or a crab that sheds its exoskeleton. So oysters do not do that. They just grow and grow and grow and grow. So if you don't eat them, if nothing eats them, they keep going for a very long time.
And kind of another question, this is more like conservation related. People are asking, if they see an oyster, should they put it back in the water? Can they survive on land? And then one question was, what can anybody do to just help protect oysters? Would it be like donating shells, or what can anybody do?
Sure. One thing that's nice to do if you eat oysters is collecting those shells. There are a lot of shell recycling programs. A lot of restaurants participate in those. The Chesapeake Bay Foundation participates in those. If you are a school that's close to the bay or one of the tributaries that has salinity, and you have a dock, you can actually put a little basket of oyster shells and help to grow oysters. So there are a few different projects that you can get involved in. But raising awareness is also a good thing to do. If you find a shell, or if you find an oyster, that'd be pretty odd, right? Because they're growing on other oysters, and they're usually not by themselves, just kind of floating around. So if you see one, I mean, you can put it back, but that one's probably already not doing so hot. And I think you had some other questions that I probably didn't answer, but regulations, I think you asked about.
Yeah, there was one about regulations about maybe regulating the population of oysters, whether that was a consideration.
Yeah, so there are regulations in Maryland and Virginia about how much oyster you can harvest each year. So Maryland and Virginia also participate in creating oyster sanctuaries. So there are areas that you cannot do any harvesting from, but there are places where the Chesapeake Bay Foundation and other organizations will take oyster shells and oyster spat and create ideal habitat for them in ways that won't be disturbed. So someone did ask if they were endangered species. They're not technically registered as endangered species. We're still allowed to harvest them naturally in the wild, but more people are moving to aquaculture because it gives them a year-round source of income instead of just concentrated in a few months. So that actually takes a lot of the pressure off of the wild oyster populations. So we're hoping that those will rebound over time.
Perfect. All right. And then back to the NG team. I have a kind of technical question of, do you use any IR cameras on your craft, and do IR cameras even work underwater?
We don't use any IR, which is infrared. So infrared cameras, for those of you who don't know, they basically look at temperature. And so in this particular application, we don't, because I think the temperature gradients wouldn't be significant enough to distinguish between oysters, because they're, I think, the same temperature as the water. And also, I mean, an IR camera would probably have some of the same problems that, you know, in water, everything gets very diffuse. So you wouldn't be able to penetrate, I think, enough of the water column. So that was not a technology we are currently using. As I mentioned earlier in the project, we had used something called LIDAR, which I'm not going to try to, I don't remember the acronym, but essentially a LIDAR is an underwater laser, a green laser in this case. And you basically shoot the laser through the water, and the wavelength or the specific color of the laser is tuned so that actually it penetrates the water column and can hit the bottom and then reflect back up. And you can measure what's called the scatter, which is basically what happens to that light. So if you can imagine, you shoot a flashlight at something, you know, that light's coming back into your eyes from the different angles. This is a similar kind of concept, but it allows you to basically look through very dirty water, which you would not be able to, or murky, which you just wouldn't be able to do with any kind of optical camera. And we demonstrated that that technology works, but we found that it's complicated, and it's not something that's easily suitable to restoration and environmental work. So someday, maybe, as it becomes less expensive, that's a different kind of sensor that we may be able to apply in this case, because it does work, but it's just complicated and difficult to use.
Okay, perfect. Beth, I saw you unmuted for a second. Do you have anything to add?
Yeah, I love that question. Can you use IR sensors underwater? As Martin said, you can, and those do exist. But I think Martin covered, yeah, that might be might not work for us in this particular situation. But I think that's a great question. You can think about, when might you perceive heat differences underwater? You know, I think of heat, thermal, right, infrared. So yeah, great question. I love the question.
Perfect. Yeah, and we've had a lot of great questions coming in. We are right at the top of the hour, so I think what we're going to try to do, I hope, to get some of these questions together in an email and send it out to everybody to get some of these great questions answered. You've really been engaged, and thank you so much for your questions. But we're gonna close it up right now. So thank you everyone for joining us, and have a great rest of your day and a great rest of E-Week. Thank you.
Thank you. Have a nice day.
Bye guys.